Thank you to AnyDesk for supporting PBS. The biggest news in cosmology in recent years is that the mysterious universe-accelerating entity that we call dark energy may be fading away. The evidence for this is now strong enough that enormous effort is going into confirming the result. So, what's it going to take, and when are we going to know? Hey everyone, before we get started, we have two fun announcements. First up, we have our second Patreon livestream with Dr. Mithuna Yoganathan of Looking Glass Universe, and it's going to be about quantum entanglement in quantum computing. The interview will take place on Tuesday, June 4th at 4 p.m. Eastern Standard Time. Joining us on Patreon is one of the best ways to support the Spacetime community, and you'll get to participate in the live stream live and get early access to the interview. And don't forget to check out the Looking Glass Universe channel. Also, June is Black Hole Month. At the merch store, we have two new black hole merch items for sale. First up is a black hole size comparison desktop and gaming mat. This 32 by 18 inch mat shows a NASA accurate comparison of the supermassive TON 618 black hole compared to the M87 and Cygnus A black holes. And next is the binary black hole orbit t-shirt and sweatshirt that shows how two supermassive black hole accretion disks would warp when viewed from near the orbital plane. There's also 10% off everything in the merch store in June. Just use the code BLACKHOLE at checkout. Links in the description. Okay, on to the episode. In the 90s, we thought cosmology was solved. The universe is expanding and slowing down under the influence of gravity. In an effort to nail down this result, astronomers tracked the expansion history of the universe by watching the flashes of distant supernovae. They found that expansion wasn't slowing down at all, it was speeding up. We don't know what mysterious influence causes this acceleration, but we've named it dark energy. The most mainstream interpretation is that the vacuum of space has a native energy to it. Quantum mechanics predicts this to be the case, even if it can't predict the quantity. This idea also gives us the simplest mathematical description of dark energy, the addition of a single number, the cosmological constant lambda, to the Einstein equations. And we saw in another video that this result is a constant energy density and a resulting exponential expansion. This simplest version of dark energy is part of the lambda CDM cosmological model, and historically it's done a pretty good job of describing the expansion history and the growth of structure through cosmic time. With lambda CDM, we thought that we were back to cosmology being mostly solved. Time to tie up the loose ends once again by refining the measurement of the expansion history to verify that dark energy is indeed constant. Many thought that the dark energy science instrument would do just that, confirm lambda CDM. It didn't. Desi seems to be showing that dark energy isn't constant at all, rather it may be decreasing in strength, which puts in doubt the whole vacuum energy thing. We first reported this result last year after Desi's first data release, when the hint of a changing dark energy was just that, a hint. Desi's second data release has now promoted this tenuous result to a confidence level just shy of a formal detection. That was a few months ago now, and so this is not a news piece about the new result. Instead, this episode is really about what comes next. What measurements can and will we make next to confirm that dark energy is changing, to better measure how it's changing, and what this can tell us about what dark energy really is. That said, a quick overview of Desi is in order. The Dark Energy Science Instrument is an instrument, it's the survey conducted by that instrument, and it's the nearly 500-person collaboration behind it all. The instrument is on the Male telescope at Kitt Peak in Arizona. It robotically places 5,000 optical fibers to simultaneously capture the light of as many galaxies. That light has traveled to us for billions of years in some cases through an expanding universe, and the signature of that expansion is imprinted in the stretching or redshift of each galaxy's light. By splitting the light of each galaxy with a spectrograph, the Desi team can measure that redshift, which encodes both the distance to each galaxy and the expansion history during that light's journey. These two properties can't be disentangled without more information, and so Desi does something else incredibly cool. Remember, we want to measure the expansion history. Perhaps the simplest way to think about it is that we want to measure how big the universe was at different times in the past. Light takes time to reach us, so light from distant galaxies carries a snapshot from an earlier time. Next, we just need some sort of structure that has expanded with the universe so we can measure the size of the universe at different times. In the case of Desi, that something is the baryon acoustic oscillations, BAOs, which we discussed in previous episodes. These are gigantic circular patterns in the distribution of galaxies on the sky. They are the remnants of sound waves in the hot dense plasma that filled the early universe before the first galaxies formed. These density waves froze at a certain size when the first atoms formed, leaving a ripple pattern in the gas and dark matter that filled the universe. The galaxies that would later form from that matter still reflect that patterning, but the ripples have grown with the universe. They now give us a powerful standard ruler to track that expansion. So, simplistically, we have redshift that encodes the subsequent expansion history from a given time in the past, and then we have a measure of the scale of the universe at those times. This doesn't quite give us an unambiguous expansion history by itself, but the combination does allow Desi to test the consistency of different models of that history, different cosmological models. In the case of Desi, the cosmological models tested include lambda CDM with its constant dark energy, as well as a particular model for changing dark energy. In that model, dark energy changes over time according to an equation given in the form of a varying equation of state parameter, something we talked about in the previous video. By itself, Desi finds that the model with changing dark energy has only a marginal improvement over lambda CDM, but things get much more interesting when the Desi data is combined with other studies. The first is the constraints from the cosmic microwave background radiation, which provides the starting point, the initial conditions from which cosmic expansion and structure formation measured by Desi will evolve. The other is an independent measure of distance. Desi itself only has the galaxy redshift as a distance indicator, which makes it difficult to pin down the absolute scale of these BAO rings. So they add an independent measure, the same type that was first used to discover dark energy, type 1a supernovae. These exploding white dwarf stars are called standard candles because they explode with predictable brightnesses. That means we can figure out how far away they are based on how faint they appear due to that distance. One way to think about it is that the supernovae give distances from us to the galaxies, while the baryon acoustic oscillations give distances between those galaxies. Standard candles plus standard rulers. Combined with the initial conditions from the CMB, these measurements give a much tighter constraint on their cosmological parameters. Desi claims that the combination favours a cosmology in which dark energy is actually weakening, and that this differs from the cosmological constant model by up to 4.2 sigma for the supernovae in Desi's own survey, but a bit less than 4.2 for other supernova surveys. This doesn't quite reach the 5 sigma level required to claim a discovery, but it's tantalizingly close. So, did Desi probably discover that dark energy isn't constant? Not really. Besides not quite hitting 5 sigma, they also test this one version of varying dark energy, which you could argue is a little ad hoc. When you're fitting a curve to a bunch of points, adding extra degrees of freedom always improves the apparent fit. That could be what's happening here. Still, it's intriguing enough to warrant deeper exploration. What we really want is a precision measurement of the way expansion and dark energy have changed over cosmic time, because that would allow us to A, be sure that the change is really happening, and B, distinguish between different models of dark energy, which in turn could tell us what dark energy really is. Now, we've talked about those options before, so I won't go into it now. I want to focus on what's needed and what's being done to improve this measurement. How do we improve the Desi result? Well, the answer is a little prosaic, I'm afraid. We just need to do everything better. Let me remind you of the three things we talked about. Now, this is an oversimplification, but it serves to organize the ideas. We need to, 1, measure the starting state of the universe. 2, to measure the size of the universe at different times. And 3, to measure distances to those different times. We'll dispense with number 1 quickly. Measuring the starting state means measuring the initial density distributions and various energetic components of the universe from the cosmic microwave background. There are plans to do this better than the Planck satellite already has, but honestly, our current CMB map is the most precise part of this whole calculation, so it's not the limiting factor. So straight on to number 2. How can we improve our measurement of the size of the universe? Well, baryon acoustic oscillations really are the gold standard, and so just doing Desi better is probably the way to go. That means we need bigger, better galaxy redshift surveys which beat down the uncertainty in various ways, including the sheer number of galaxies. We also want to push the measurement back further in time, which we can do with more sensitive instruments on bigger telescopes or just staring at the sky for longer to collect photons from fainter galaxies. And 3, we also want to improve our measurement of distances to those galaxies. The most obvious thing is to improve our supernova measurements with more Type 1As, but also by refining our calibration of these things as standard candles. This is one of the most contentious points in the whole effort because the supernova distances piggyback off a chain of distance measurements, and so errors can have crept in unnoticed in various places. Major efforts are underway to weed out potential issues. It's also important to find independent ways to get those distances. One of the most exciting and a personal favourite of mine is to use gravitational lensing. Gravity bends space, and so bends the path of light. Very strong gravitational fields, like those of entire galaxies, bend space so much that the light from a distant source can travel to us via multiple separate paths. For example, distant quasars feeding supermassive black holes sometimes appear duplicated or even quadrupled around a galaxy that happens to lie directly between us and it. Now, when that quasar fluctuates in brightness, all of these lensed images also fluctuate because they're all the same quasar, but the pattern of fluctuations has an offset in time that reflects the difference in the lengths of these paths. Measuring this time delay actually gives us a measure of the cosmic distances that's completely independent of the supernova measurements. Astronomers have used a handful of lensed quasars to measure the expansion rate of the whole universe, but by doing this for many more such objects, we can also get the expansion history. Now, I was being a little simplistic when I separated the ideas of measuring the size of the universe at different times to measuring the distance to those times. Really, any given cosmological measurement does some of both. For example, we track the size of the universe just by looking at how far apart galaxies are in general, not just the size of the BAO rings. So this size information is also there, for example, in the supernova catalogues, even without the BAO analysis. And the expansion history is coded in the redshifts, so we can calculate expansion rates even from just, say, the lensing time delays. But really, combining these data sets is the key. What we're trying to do is fit a cosmological model with many interacting or covariant parameters. So we need measurements that will tease apart and constrain all parameters. And on that note, there is one parameter that I haven't mentioned, and that's the clustering of galaxies. Over cosmic time, galaxies are thrown apart by cosmic expansion, but they also fall together due to their mutual gravitational attraction. The amount of this clustering tells you stuff about the amount of dark matter in the universe and the size of the initial density fluctuations, both important parameters in your cosmological model. So measuring this clustering is a big help in constraining that model. Galaxy redshift surveys like Desi can do this directly to some extent based on the clustering of the galaxies that they can see.
But there are also more cunning approaches that can take account of all the mass, seen or unseen. For example, through weak gravitational lensing. The lensing I already talked about, where you see multiple images of one object, is called strong lensing. In weak lensing, the gravitational field of galaxies and clusters slightly warp the shapes of background objects, without actually producing multiple images. In the case of a weakly lensed galaxy, it'll be slightly stretched in one direction. You can't identify the effect with a single galaxy because you don't know what shape that galaxy was originally, but imagine many galaxies in a particular direction that normally have random orientations relative to each other. As their light travels to us, it passes around, let's say, a particularly dense patch of the universe. The orientations of all those galaxies will be skewed at right angles to that patch and become correlated with each other. By looking at the correlations of galaxy shapes across the entire sky, you can get a crude density map of the universe, which in turn allows us to constrain galaxy clustering.
The Desi result that made all this news is from their second data release, 3 years into the 5-year survey, and with 30 out of the planned 50 million galaxies, and quasars actually. If the deviation from constant dark energy is real, it seems likely that this extra signal will get them over the 5 sigma level. But Desi is not the only game in town, nor the only thing needed to reduce that uncertainty. We should not confuse Desi with DES, for example. That's the Dark Energy Survey. DES observes a factor of 10 more galaxies than Desi, but where Desi takes spectra of known galaxies, DES takes images at different wavelengths and actually discovers galaxies. That makes DES an imaging or photometric survey, where Desi is a spectroscopic survey. DES measures photometric redshifts, which are less accurate than Desi's spectroscopic redshifts, but take much less time to observe. DES also doesn't see as far as Desi, so isn't sensitive to the expansion history. Instead, DES is good at measuring the late time expansion rate, as well as the growth of structure via clustering and weak lensing measurements. It's also important for nailing down them pesky supernovae. Really, DES is complementary to Desi, giving the late time constraints, just as the CMB gives the initial conditions. But perhaps the greatest improvement on these results will be from very new and upcoming surveys. We have the European Space Agency's Uklid satellite, which is studying over 1 billion galaxies with both imaging and spectroscopy, and its most important cosmological contribution is by measuring galaxy clustering and weak lensing. This should allow us to beat down the uncertainty in the equation of state parameters to the 1% level, which moves us toward a precision measurement of dark energy. Uklid is in the first of its 6-year mission, and the first cosmological results are expected next year. And the last, and perhaps for me most exciting endeavour, is the Legacy Survey of Space and Time, LSST, on the Rubin Observatory. This is a photometric survey that does something very new. It'll map much of the southern sky many, many times for 10 years. Besides complementing or improving on Desi, DES and Uklid, LSST will add the dimension of time to the analysis. Perhaps the most important benefits to cosmology are the measuring of many hundreds of thousands of Type 1a supernovae, providing an incredible late-time anchor for the other surveys. LSST will also enable measurement of those time delays in the gravitationally lensed quasars, which, if you remember, give us an expansion history independent of supernovae. But LSST will only do this after discovering something like 20 times more lensed quasars than we currently know of, so this method should really come into its own with LSST. We are entering the era of precision cosmology. It's really a golden era for the field, and in this next decade you can expect the cosmic expansion history and the general cosmological model to become known to a precision that seemed impossible not long ago. With that precision comes the ability to ask what kind of physics can produce such a universe? What kind of dark energy, dark matter, starting conditions? And what does that mean for how the universe will end? We will know it all just as soon as we've finished surveying all of space-time. Thank you to AnyDesk for supporting PBS. AnyDesk was created because whether you're in a remote location or just working from home, the need for reliable, secure communication and data transfer remains important. With AnyDesk, secure direct file transfer bypasses the cloud entirely, allowing you to move large media files, benchmarks, logs, or firmware updates between systems. And when you're working on that groundbreaking research, AnyDesk knows you don't want any interruptions. AnyDesk offers very high uptime reliability for stable connections, uninterrupted remote access, whether you're managing builds, servers, or checking telescope data. Plus, AnyDesk is built with their proprietary codec DeskRT technology. This helps ensure minimal latency and crisp visuals, even over slow or unstable internet connections. AnyDesk is available for personal use, but if your research requires a lot of global communication, AnyDesk offers custom-tailored business plans. To learn more about AnyDesk, go to anydesk.com/spacetime or check out the link in the description.